So what are the three elements we have in the hand? First, there is an inescapable error we are going to make. Well, what should we call for the error? I mean, we could make 10%, 5%. Well, naturally enough, we want to introduce an algebraic notation for it. Let us call the error after the formidable Augustin Louis Cauchy, who introduced this notation in 1821. Let's call it epsilon, the Greek letter. Of course, the epsilon is standing for an E for error. What about the confidence? Well, we can only say that we'll make an error no more than this with a certain confidence. Let us say we call the confidence 1 minus delta. And what do I mean by this? Well, if I want a confidence of, say, 90%, then I want delta to be 10%. If I want a confidence of 95%, I want delta to be 5%. So here are, for example, samples of what epsilon and delta could be. So epsilon is 0.03 says that I make an error of no more than 3%. A confidence of 95% says that delta is 0.05. So this pronouncement will say that I'd like to say that I make an error of no more than 3% with a confidence of 95%. Or, in other words, I make an error or exceeding 3%, the chance of that happening is no more than 5%. Here are other possibilities for epsilon and delta. For example, an error of 1%, epsilon is 0.01. A confidence of 99%, delta is 0.01. Or, yet again, an error of 5%, and perhaps a confidence of 90%. Epsilon is 0.05, delta is 0.1. It would be wise not to make an absolute pronouncement on what epsilon and delta should be ahead of the fact. Different settings need different error tolerances and different confidences. For example, a setting involving, let's say, the number of misplaced letters by the postal service requires a certain error tolerance and a certain confidence, right? Perhaps one cannot get away with misplacing more than, let's say, 1 in 100 or 1 in 1,000 letters, right? Otherwise, there might well be a revolt on the streets. But if the setting is that of, let's say, space exploration, then an error of 1 in 100 or 1 in 1,000 could be catastrophic. Right? The moment one lets a spacecraft go, it is beyond our reach, and we have a very small tolerance for error. And so in those cases, an epsilon might need to be very tiny, maybe 1 part in a million or even 1 part in a billion. So the moral of the story is that we should not restrict what epsilon and delta should be a priori. We should let the problem inform us how much error is tolerable and what confidence is desired. The third element, of course, in this program is the amount of data available, the sample size n. And of course, these three quantities are ineluctably linked. And so here is a $1 million question. If one is given, let us say, a maximum error tolerance epsilon and a desired confidence that the estimate is within that error tolerance of, say, 1 minus delta. For definiteness, if the reader wishes, she can think of epsilon as, say, 3% and delta as 5%. So we're talking about a no more than a 3% error with a confidence of at least 95%. What size of sample will guarantee these error and confidence parameters? All right, let's set it up now mathematically, because now we want to make quantifiable progress at estimating this. Recall, what do we want? For the desired sample size n, we want the relative frequency of successes, Sn divided by n, to be, on the one hand, no smaller than p minus epsilon, and no larger than p plus epsilon. For definiteness, if p is 0.6 and epsilon is, say, 10%, 0.1, then I want my relative frequency to be no smaller than 0.6 minus 0.1 or 0.5 and no larger than 0.6 plus 0.1 or 0.7. So with this in hand, here is our desired relation. The probability that the relative frequency of successes, lies between p minus epsilon and p plus epsilon should exceed 1 minus delta. So what this is saying is this: if this kind of guarantee can be provided, let's say epsilon is 3% for definiteness. Let's say that 1 minus delta is 95%, delta is 5%. If we can proffer such a guarantee, then we are saying that if we do the random experiment and we generate whatever is NAs and generate the sample of that size and generate the relative frequency of successes Sn over n, then this relative frequency of successes will be within 3% of the underlying p, which is not known to us. But it'll estimate p by no more than a 3% error. And this will happen on average at least 95% of the time. Very roughly speaking, if 100 people did polls, each of them reported a relative frequency of successes, on average, 95 of them will get answers within plus and minus 3% of the right answer. And of course, unfortunately, sadly, 5% of this group, 5 of these 100 on average, will get answers out in left field. We have no idea where the answers could be. They could be very bad, very big, very small. We'll have no confidence whatsoever in those answers. Of course, we'd like to know ahead of time whether a particular sample is good or bad. Sadly, we cannot proffer any absolute guarantees. We live in a chance-driven world. Bad things happen to good people. Life happens. And so, all we can say is the following, that if a random experiment is performed, then a large percentage of them, say 95% of such experiments, will give good answers. But we have to live with the sad reality that our particular experiment might be bad. But this happens rarely, and we can take solace in that. Now, this is an adequate statement of what we want, but let's try to compact it mathematically. What this is saying is that Sn over n, the relative frequency of successes, differs from p by no more than epsilon, either on the negative or on the positive side. And therefore, by the expedient of taking absolute values, we can simplify this expression and write it down as the probability that the absolute value of the difference of the relative frequency of successes from the underlying probability p is no more than epsilon. Or, yet again, if the relative frequency of successes differs from p by no more than epsilon with probability 1 minus delta, then the probability of the obverse event, the complement, should not exceed delta. And so this is equivalent to saying that the deviation of the relative frequency of successes, Sn over n, from p, in absolute value, exceeds epsilon with a probability no more than delta. This has got, of course, many moving parts here. There are epsilons, and there are deltas, and there are n's, but at least we have a compact expression to look at. Now let's take a look at this and see what we can do with this. So here is our desideratum. We are given, a priori, an error tolerance epsilon. We are told that our estimate should lie within that error tolerance with a confidence of at least 1 minus delta. Here is a simple mathematical condition to check. And now it is clear that in that equation is buried a relationship between the error, the confidence, and the sample size. As I mentioned earlier, the error, the confidence, and the sample size form an intricate walls in this process. They are intimately connected. Okay. And the heart of the connection is a mathematical relation which is buried in that relation. This is what we would like to extract.